Artificial neural networks are mathematical machines. The biology can only get us so far. We really need math to extend what we get from the biology into a useful algorithm. And the deeper the math that we use, the better the network we actually will be working with. So math and psychology, actually. There are two questions that we can't answer biologically. What type of network we should use? The network topology of real-world neural networks is just far too complex. And how do we estimate synaptic weights and these thresholds theta sub j? We'll start with the first, and we'll see that as we learn more, the answer to these questions will change. So we'll get something that works, but then as we learn more, as we refine more, as we do deeper and deeper mathematics, these answers that we're going to get in this lecture will be modified. So first off, we could say, well, let's suppose we looked at a minimally connected network, a tree. So for instance, we could use a decision tree where logistic regression is used for each decision. That is a neural network. And as a matter of fact, it's something that's kind of fun to set up, is instead of using information gain at each node, use logistic regression at each node. But what we'll find out in such a case is that such an artificial neural network is actually a linear classifier. And training would be via maximum entropy, and we don't necessarily have any indication of maximum entropy training in our own brains. So minimally connected may not be the best approach. We don't escape linear. What about maximally connected? This actually has some utility. So we're going to look at an artificial neural network on a complete graph with a discrete firing function. And in particular, we're going to look at what are called Hopfield networks. On will correspond to 1, and off will correspond to -1, not 0. And so our firing function is actually going to go from -1 to 1 at some threshold theta sub j. And we'll be completely connected. It's a complete graph. And we're going to assume symmetric weights. So wij is equal to wji. And the Hopfield network fires randomly. So we'll go through and randomly choose a neuron, and we'll update it, and then randomly choose another, so on and so forth. So we can look at this thing, Hopfield network, in terms of matrices, our inputs. There's one input for each neuron, and it's also the output from the neuron and the input to the other neurons. And each x sub j is either 1 or -1. And the weight matrix is just all the synaptic weights. The neurons are not connected to themselves, and it's a symmetric matrix. Now, we're going to use Hebbian learning. Learning will correspond to modification of the synaptic weights. And we'll do so using what's known as a Hebbian learning rule. We get this from the cognitive psychologist David Hebb, who came up with a learning theory based on the idea that learning takes place by reinforcing connections among learned states. So to learn a pattern, so we want the network to be able to recall this pattern that we're going to give it, then we're going to have each entry in the pattern be either a +1 or a -1. We're going to fix a learning rate, and then we're going to update what we had previously for the synaptic weights using this very simple rule. The new synaptic weights will be the old synaptic weights plus epsilon times p sub I times p sub j. In matrix form, we're actually looking at what we would call an outer product, a column times a row, and this gives us our Hebbian learning matrix, except down the diagonal we have p1 squared, p2 squared, so on and so forth. Each one of these is a 1, however, so that means that we can subtract the identity matrix, and that will remove the diagonal, so that our matrix form rule is the new matrix will be the old matrix plus epsilon times P dot P transpose minus the identity. A simulation begins with an initial state, after which we select a neuron at random and fire based on this firing rule. Notice here that I will not be equal to J, so the neuron's not connected to itself. And we repeat until hopefully something useful happens. We're going to look at this in terms of letters in some sense. So we're going to have these rectangular grids, and blue will correspond to a 1 and white will correspond to a 0. But remember that our 0 here is actually a negative 1. So blue is 1, white is negative 1. Or we can think of this: blue is true and white is false, and we're using negative 1 for false. Now we imagine complete connectivity with all these weights. Now, I haven't shown all the edges here. We just want to imagine that every single one of these rectangles is connected to every other rectangle. And then we want to choose the ith neuron at random and calculate its new state. So here's an actual simulation of that. We'll take our input pattern. This is a T. We'll learn that input. And let's teach it another one. So this is using the Hebbian Learning rule. We're updating that matrix using this matrix learning rule to update that synaptic matrix. So we've learned a T and a C, and here we go with an I. So we can learn that. And so now we want to see if we can recall. And so we put something in, and notice that we're not going to put exactly in, but we're going to say, that sort of looks like an I. And so now we're going to fire 10 neurons at a time. And you'll notice that what happens, let's go to 100 at a time, is as we randomly choose, we get something that settles in to one of the letters that we've learned. So we learned the letter C, and as we randomly select and fire, we call that asynchronous, then we end up with this. Now the Hopfield network has an energy, and the energy is defined as you see here. And there's a theorem that the energy decreases each time a neuron fires. And let's actually prove that. So if we take the new energy minus the old energy, so after we've randomly selected a neuron I, then only the x sub i's can change because we selected an x sub I at random and everything else stayed the same. So therefore, in that double sum, all we're left with is the x sub I term. So we can see that in this double sum, that the only thing left from the double sum will be the x sub I. Now, notice that we have a negative here out in front. That's going to be important. Now let's suppose that the new value of x sub I is greater than the old value of x sub I. Well, that will imply that the first term is positive. It'll also imply that the sum of the weighted inputs was greater than the threshold, which will imply that the second term was positive. And so therefore, E new minus E old will be a negative times a positive, and that implies that E new minus E old is negative, or that the energy decreased due to the firing from what it was previously. The other case is that the new value of x sub I is less than the old value of x sub I, in which case the first term is negative, which implies the threshold was larger than the weighted sum, and therefore the second term was negative, and therefore we get the product of three negatives, and once again the new energy is less than the old. So in either case, we get less energy or lower value of the energy. So let's look at this in action. So now when I learn things, it's actually going to show us what the energy is. So there's the energy for learning the letter T. And now let's learn the letter C. And notice when we hit the Learn button that it's going to have an energy, negative 4498. Notice all these energies are negative. And now we're going to look at the I. So we'll learn the I. And once we've learned the I, then once again we get a negative energy. So if we recognize, or if we want to see if we can recognize, we think that looks like an I, don't you think? Well, let's randomly choose neurons, and notice what happens after 10 is that the energy is going down from the initial input pattern. And in particular, it's going to keep going down until it reaches a final value corresponding to something that we've learned. So this works no matter what pattern we put in. We're going to start at a higher energy, and as we asynchronously choose neurons at random and fire, then it's going to settle in. Notice we also begin to see a problem here, because we might have said, well, that looks like a C, but in reality it thinks it's an I. And the problem is because we have an energy surface, this is in n dimensions, which can have spurious states and can also have rather broad valleys for some patterns, but narrow valleys for other. But we're going to focus on the spurious states concept. We learn some kind of a pattern, in this case the T, and then we learn, say, a C, and so we got another minimum. And then we also learn an I, and we got another minimum. But in the course of learning these letters, we start introducing other minima, local minima. And these local minima are places where the network could settle into, but they're not things that we actually wanted, that we taught the network. They're spurious. They just popped up. So can a Hopfield network correctly predict the class of any trained pattern? In other words, can we get f of pattern equals class to some high degree of accuracy? No, we can't. And the reason is that the more we train with these patterns, the more the spurious states can overwhelm what we've learned, so that we eventually will have lack the ability to correctly recall what the network was taught. Now, let's look at an example of that. So I'm going to teach it a new letter. I'm going to teach it the letter H. And so I teach it the letter H using our Hebbian Learning rule to change the synaptic weight matrix using P transpose minus I. And now let's suppose we want to recognize something. And so we do that. That thinks that's an I. Okay, we'll give it that. And now let's suppose that we say we want to learn something else. Recognize something else. Well, it thinks that's an I. So it's got a wide valley for the I. So it really kind of thinks everything's an I. And if you'll notice, that's because we've reinforced the upper and lower part of the I with 3 different patterns. Now we enter this input pattern, and it converges to something that we didn't teach it. In fact, it's pretty easy to recreate this spurious state. We just make a C, and anything that looks like a C with some extra stuff is going to converge to this spurious state that's got the extra thing there. And you can see that. I'm going to put some junk in here inside the C, and if we run it, and run it, randomly selecting neurons, 10 at a time, now 100 at a time, and it converges down to a minimum energy. But this is a local minimum. This is a spurious state. This is not something we actually taught the network. So what is the best network? Well, we have to turn to mathematics to get that answer.